But let's go. So hi everyone, my name is Abdel. I'm a developer advocate at Google. You probably know me from the Kubernetes podcast. If you don't listen, I will give you 5 minutes to sign up. I'm just kidding. I'm also co-chair for Kubernetes and I do a bunch of other stuff on the side. But the goal of this presentation today is to talk about where Kubernetes is in terms of like resource management in general. So we called it pod right sizing in the second decade of Kubernetes because there's actually a lot of things happening within the Kubernetes open source to make scheduling workloads easier. I'm gonna spend a couple of minutes actually kind of give you a primer. So for those of you who know how Kubernetes works, probably this is gonna sound familiar. But for those of you who don't, this probably would serve as a good refresher. So you're already familiar with this. You deploy a pod and then you set your resource requests or limits on the container level. What Kubernetes will do during scheduling is just it will add up all the request limits and all the resource requests and limits for all the containers within the pod. And then that becomes the resource requests and limits of the pod itself. And then it will make its scheduling decision based on that, right? So resource requests are used during scheduling time. So that's actually what Kubernetes used to find a node that can fit your pod. And limits are used at runtime. If a pod exceeds its limits, it's either be evacuated or throttled depending on which limit it exceeds, whether it's CPU or memory. One of the new things that was introduced in Kubernetes 1.34 is actually pod level resource requests. So it's not at the container level anymore, or not only, you could actually assign pod resource requests and limits at the pod level, and then those are getting shared between the containers in the pod, right? So that's a new introduction that was introduced in beta in 1.34. How does this resource requirements, like when you set the requests and limits, how do they translate at the container level? Well, it's very simple. When you set your CPU requests, well, those are going to get translated into a share of the CPU. So a 0.25% CPU or 250 milli CPUs basically means 1/4 of a core. Or if we're talking about it as runtime over a minute, that's like 1/4 of a minute. That particular container or process can use the CPU. But the limits are actually set in terms of CPU quotas. Because each CPU has quotas, the OS is aware of how much resources that particular CPU can fit. And then the requests are expressed on type of quotas. The point here is that CPU requests and CPU limits are all translated into time, right? So how much time the pod can use the CPU for. The quota side or the limit side, that's essentially the headroom, so how much time is left on the CPU will be shared across all the processes with very particular quotas. So the more a process exceeds its CPU limits, in particular for containers, the more it eats up from that headroom. And then it will impact the other containers running on the same node. Memory is very straightforward. It's just translated in terms of bytes, right? So how do we right-size a pod, right? The million-dollar question. They're kind of like, depending what you are doing and depending which parameters you set, you're going to end up in 3 different situations. Either in what we call a guaranteed situation, where you are actually setting the limits and the requests. So that means that the Kubernetes will guarantee that the requests are available at the scheduling time, and it will also guarantee that your pod is not going to exceed its limits. So that's the guaranteed part. If you set no limits, then you are in what we call a burstable situation. Burstable means that the pod can burst up to whatever resources are available on the node, right? And then best effort is when you don't set anything. That's YOLO mode. You just set the pod, no request, no limits, and then the pod will just work. Now, there have been actually some changes, both in Kubernetes open source and in cloud provider-specific hosted platforms, where in Kubernetes open source, if you don't set the limits, nothing will happen, or the request, nothing will happen. But if you're running, for example, on top of a fully managed Kubernetes environment, like Autopilot by GKE or the Auto Mode by AWS, then both platforms will actually have an admission webhook, a mutation webhook that will modify the requests to set them. Because when you're running on top of fully managed Kubernetes, you're not actually paying for the nodes, you're paying for the pod resources. So the cloud provider decides if the user doesn't set requests, I'm going to assign some default requests, which are typically around like 50 megabytes and 50 milli CPU. So if your pod exceeds its CPU limits or its resource or memory limits, 2 things can happen. If it's memory, the pod will be evicted because memory is not a compressible resource, right? But if it's CPU, the pod will be throttled. And it will be throttled up to the point where the node experiences pressure, and then some of either the lowest priority pods or a random pod will be killed. Kubernetes doesn't have really a concept of Like the only way you could guarantee that your pod will be throttled and killed first is to set a lower priority, because that's the priority is actually set as a parameter to the scheduler that decides, and the kubelet also that decides which pods to evict first. If your pod, for example, had a pod disruption budget, but it's still throttled, it's not going to be evicted first. It's the pod that doesn't have a PDB or doesn't have priority class that will be evicted first. So here's an example. We have a node which has 4 gigabytes of memory, sorry. It has a pod running which requests 1 gigabyte, so that's guaranteed. Then there is a second pod which is not setting a limit. So the first pod has a limit of 1 gigabyte. The second pod doesn't have a limit of 1 gigabyte. So it's basically be able to burst to the extra memory available on the node, up to the point where a new guaranteed pod is scheduled. So the more guaranteed pods, which means pods that have resource request and limits, are scheduled on the node, the more they eat up from the headroom of available memory. Up to the point where if that particular burstable pod keeps eating up the memory available on the node and it exceeds a certain threshold, usually Kubernetes doesn't allow actually a pod to go up to 100%. It will set it to something like 90% of the memory available on the pod. Also, because Kubernetes will set some resources on the node for the system components, right? That's why when you do a kubectl describe on the node, you have allocatable and available. So available is the total amount of resources available on the node, and allocatable is what's available minus what have been set for daemon sets, kube system, pods, things like that, like the core components, kubedns maybe, and things like that. So yeah, if CPU is overrun, your pod will be throttled. Very simple. So now, is there a better way actually to handle this dynamically? But we all know that basically, probably you know that it have been historically not possible for you to resize a pod live. If you want to resize it, you will have to kill it, edit the requests and limits, and then redeploy it. That's not the case anymore since Kubernetes 1.27. So since Kubernetes 1.27, Kubernetes introduced something called In-Place Pod Resize, IPPR. So In-Place Pod Resize allows you to basically live change resource requests and limits. Now, the question is, can I actually change up and down? Obviously, you can increase the amount of CPU and increase the amount of memory, both on the requests and limits, but you can decrease CPU, but you cannot decrease memory because you don't know which pages of memory are being used. So technically, you can scale up, but you should be very careful when you're scaling down. So that can be done simply by just using, so the way that's done is through a set of new fields in the pod spec. Like for example, the resize policy, which defines what happens when I resize CPU and what happens when I resize memory. I can either set it to restart or not required. So not required means the pod window be restarted. And then that gets reflected in the status. So when you resize a pod, the status will reflect that it's in progress up to the point where it's resized. A question that I get often is, what happens if I resize a pod and there are no resources available on the node for that particular resize I'm trying to do? Well, the pod will be stuck in progress. It will continue running. It's not going to be evicted, but the status will just reflect in progress indefinitely, or up until either resources get freed up on the pod and the kubelet can resize the pod, or the pod itself gets killed and then moved somewhere else, right? So the way we would do it is by doing kubectl. Okay, so we talked about this. Basically the 127 made resource requests and limits mutable. They used to be immutable before, so you can change them, and then added this resize policy. And then you can just do this simply by running a kubectl patch. If you want to do it live on a pod which is already running, you just kubectl patch the pod. Obviously, if you are using a CI/CD pipeline with GitOps, you will want probably to do it through your GitOps pipeline, where you modify the YAML files or whatever templates you have, and then you reapply them. And even if you actually kubectl apply the YAML files, the deployment, well, the pod will not be restarted if the policy is set to not required. So kubectl patch, and then you can patch whatever container you want live, and it should just work. You can actually try today by just creating a cluster, ideally 1.33 plus, because the feature now is in beta in 133. In 127, it was alpha, so you have to turn on the alpha gate in order to use it, right? Well, this actually, the cool thing about this is that it opens up a lot of very cool possibilities in the future. And one of the ones that I'm super excited about is being able to actually use a pod autoscaler to do what we call a CPU boost. So if you have run workloads on any sort of container as a service platform before, like AWS Fargate or Azure Container Services or Google Cloud Run, they all support something called CPU boost. So you deploy your container in the cloud, and then you set a CPU boost feature, which the cloud provider says, okay, I'm gonna give you double the amount of CPU for the first 2 minutes for your pod, for your container to start. And then I'm gonna take it out, right? Why this is interesting, it's interesting for workloads that needs actually a lot of CPU at boot time, but then they don't need it at runtime. Typically, in order to accommodate this kind of use cases, you will just oversize the pod because you want the pod to start faster. And here, I'm gonna look at the room and look at the Java developers who know what I'm talking about, right? Because a GVM type workload usually requires a lot of CPU because it has to do a lot of calculations, a lot of class optimizations at the beginning, but it doesn't necessarily need those CPU cycles when the application itself is run. So instead of oversizing the pod, you could just basically boost it, which means give it more CPU cycles when it's starting up to a point, and then you take away the CPU cycles, and then you let the app run with whatever resources it needs. So this today is a proposal upstream, and it's proposed as a change into the VPA API, so the Vertical Pod Autoscaler API. If you don't know, the Vertical Pod Autoscaler is basically like HPA. It just scales up vertically instead of horizontally. Up to today, VPA, the way it works is that it will restart the pod, right? You set a VPA object, you set a selector to say which pod it should target, and then you give it a threshold. And the current API has basically 2 modes. There is what we call auto mode, on or off. If you set auto mode to on, VPA will restart your pod. It will kill the pod and resize. So it will monitor the pod through the metrics server. And then if it realizes that the pod is actually using more resources than it initially requested, it will restart it and change the resource request of that particular pod, right? If you set the auto mode to off, it will not touch the pod. It will just reflect in the status of the VPA itself recommendations. It's what we call recommendation mode. So if you kubectl describe the VPA, after you let it run for a while, it will say, hey, this pod is using X amount of CPU, but its resource requests are set to lower. So I would recommend you to restart it. So that's the current VPA. The future one will look like, so yeah, this is how the current VPA looks like, the V1 version. You see update mode off. So if you set it to off, it's not gonna do any updates. If you set it to on, it will update the pod, right? So updating obviously means resizing. We just talked about that. With In-Place Pod Resize, what we could do basically is we could make the VPA give the pod extra resources. So when the pod gets deployed, if there is already a VPA in the cluster, then the VPL will intercept that. It will change the resource requests, deploy the pod, and then after the pod is deployed for a while, it will patch it and take away those extra CPUs it gives it. So that's CPU boost. So we have actually done some tests. We have an implementation of this. So this is what we call VPA 1.5, which we are contributing upstream. Google is contributing upstream. I think that the cap, I forgot the name of the number, but the cap have been accepted. They're working on it. So there will be a new version of the VPA API coming, which will have this CPU boost feature. But we have a proprietary version running on our platform that we have tested. And this is the demo I wanted to show you. So here is an example. What you are seeing is on the top, I have a shell environment where I'm deploying an app. Second window, I have my Spring Boot demo app running. The third window, the third one, just pay attention to resource CPU requests, CPU limits, memory requests, memory limits. And then the bottom is just logs. You can ignore it. So this is, let's start with, sorry, go back. Okay, let's start with a standard Java application with no CPU boost. So you see, we deployed it. It says running, but nothing is ready. And let's look at the minutes. It's going to take roughly 40 seconds for that pod to be flagged as ready. So now at some point, when it hits like the 40 seconds, it will flip here to 1 out of 1, which means one of the readiness gates or readiness probes have passed, right? Now, pay attention to with CPU boost. You see in the bottom what happened. The moment the pod got deployed, its CPU requests have been increased to 2 cores, and then its memory limit have been increased to 5 gigabytes. And now if I wait for a few seconds, which should be less than the previous case without CPU boost, I think it takes roughly around like 11 seconds. Pay attention, they will just be scaled down, right? So the VPA object will just patch the pod and then take away the extra CPU that was assigned. And you see here, after roughly 11 minutes, the pod is already ready. So with a very simple demo, Spring Boot 3 demo app using standard JVM, we can basically cut startup time by almost a factor of 3x. Make sense? Yeah. Sorry, I made a mistake. In this case, we're not scaling memory, we're just scaling CPU. Yeah, it's just CPU, it's not memory. Yeah. Let me go back 1 second. I realized when I was talking that I said memory, and that was a mistake. What you are seeing here, it's, let it run for a second. It's CPU requests and CPU limits, not memory. We're not touching memory. Make sense? All right? So this demo is using our version of VPA, which again is a proprietary implementation, but this is being contributed upstream. So eventually in the next, I think that the aim was to get it ready for 1.36, which was released in April, but the cap have slipped, and it would be probably available in the next version, which would be 37, which is coming in August this year. There will be an alpha version of the new VPA with CPU boost, so at least you can experiment with it. If you're running on Google Cloud, you don't have to do anything. You can just create a GK cluster and this will just work. It's already available out of the box. I think it's a checkbox when you're creating the cluster. But the point here is this will be available. So we did some extra tests with other programming languages. With Go, we can actually scale up both on CPU and on memory. With Python, we can scale up on CPU. Memory is kind of meh, but it works. And then Java, of course, it works. So Java, there is this asterisk that says no, because Java has multiple possible implementations. So if you're running a JVM, a standard JVM, you will be able to resize memory as long as you set the JVM flag to be a percentage of the container memory instead of a fixed value. You know, when you're setting a JVM flags, you can set the JVM memory to a fixed value or to a percentage. So you have to set it to be a percentage, like 90% of the container memory. And the JVM is actually container aware. So it knows it's running inside the container, and it will continuously read the memory available in the container and adjust the JVM memory to that, right? If you're running other we just tested with like standard JVM, it works. I haven't tested with other versions. And if you're running something like a native Java application like GraalVM, it will just work because there is no JVM basically in that. And then with the CPU, with C++ and Node.js, it also just works. You can resize memory and CPU. Now, actually, I'm almost done with my slides, okay, so 5 minutes. All right, so there is one more thing that I want to talk about, which I think is very cool. It's this upcoming thing called Workload Aware Scheduler. You should go look it up. There is an article on the Kubernetes blog about it. So this is a new API. So the Workload API is a new API coming to Kubernetes. It's not a single API. It's multiple things under the hood, and they are in different stages of like alpha, beta, and GA. The Workload API itself just went beta in the last version of Kubernetes. And what the Workload API is, it's essentially a solution for the use cases where you need to make sure that a set of pods are either all scheduled or not scheduled. So a transactional way of scheduling pods. Today, the way the scheduler works with Kubernetes specifically is that it evaluates pods one pod at a time. So if you have an influx of pods coming that needs to all be scheduled, the Kubernetes scheduler have an infinite loop and it will just evaluate each pod at a time. But sometimes what you need to do is you need to make sure that a set of pods that are part of the same logical application, think database, think inference for AI, stuff like that, you need to make sure they're either all scheduled at the same time or not, right? So with Workload API, which is an abstraction layer, so it still uses the pod API under the hood, it has a new intermediate API called pod group. And then in the pod group API, there is a scheduling mode called gang scheduling, which is what you see on the left. So gang scheduling just basically means that the scheduler will evaluate all the pods which are part of the pod group. And if it can schedule them, it will do. If not, it will just keep them to pending. Make sense? The use case here would be that if you have 10 pods which are part of the same application, and then the cluster starts scheduling them one at a time and run out of resources, it will just stop, right? With gang scheduling, either you make sure they all get scheduled or not. The second thing is this thing called workload aware preemption. So preemption is essentially when the pod needs to be killed for whatever reason. Workload AI preemption allows you to actually create dependencies between pods. The same way you schedule them, you can also make sure to tell the cluster, hey, these pods are part of the same group. So either preempt all of them or none. So this would be use cases for a sharded database. You have a database running across multiple pods, and you need to make sure that they're all either running or none is running. Because half of your database pods running means half of your database is available, which is not what you want. And then the third thing, which is topology-aware scheduling. So this have actually existed in Kubernetes for a while. There is improvements into it. So what topology-aware scheduling allows you is that it allows the scheduler to be aware of the layout of the cluster. The simple example would be you have a cluster with 3 nodes in 3 availability zones. I want to tell the scheduler, schedule 3 pods, but make sure they are all in each node. So that's all my pods doesn't end up being on the same node in the same availability zone, right? A second use case would be if I am scheduling 2 pods that talk to each other very often, I can tell the scheduler, make sure they land on the same node because I cannot afford the internode latency, right? Things of that nature. So these 3 APIs or these 3 kind of use cases are all being kind of wrapped under the workload API. Just to be very clear about something, this is not changing the APIs inside Kubernetes. The standard low-level objects that you are familiar with, like the pods, replica sets, jobs, deployments, all of that stuff is not changing. Workload API is just a higher level abstraction which utilizes these underlying APIs. And with that, I want to talk about one cool thing. This is unrelated to Kubernetes scheduling. There is this new community that we just started. I'm one of the ambassadors. It's called Merge Forward. This is a community trying to actually build the future where everybody can contribute to open source. I highly recommend you check it out. There is a Slack channel called Merge Forward. And then there is multiple subgroups within the Merge Forward. So if you are within an underrepresented group or you don't feel you are represented in the cloud native space, maybe Merge Forward can be a way to feel some sort of belonging or representation. And with that, I would say thank you so much, and I hope this was useful.